Imagine this. You're strapped into the left seat of a Citation Sovereign, those powerful engines humming as you prepare for takeoff. It's a remarkable piece of aviation, isn't it? A real high-performance jet designed for speed, comfort.
Oh, absolutely. A fantastic machine.
But with the incredible privilege of commanding something like that comes the absolute necessity, the need to know its every secret, especially, when things don't go perfectly. Today, we're doing a deep dive specifically designed for you, whether you're a pilot, maybe prepping for that all-important check ride, or maybe you're just someone intensely curious about the rigorous knowledge required to fly these incredible aircraft safely.
Yeah, the level of detail is pretty intense.
It really is. So we're going beyond the usual overview and stepping into, well, a simulated mock check ride for the CE-680 Sovereign, our mission, to distill the most critical emergency procedures and operational limitations, pulling them right from the official training materials.
Giving you that vital shortcut, basically.
Exactly. A shortcut to being truly well-informed about this magnificent machine. So think of me as your examiner for this session, okay? I'll be throwing out scenarios, asking the precise questions, the kind of things a pilot would face under scrutiny.
And I'll be in the hot seat, trying to give the answers.
Right. And our expert here is going to provide those absolutely essential answers, adding the kind of clarity and, crucial context that transforms just raw facts into deep, ingrained understanding.
It's a fantastic way to approach this material, actually, because what we're drawing from here are Flight Safety International's memory flashcards.
The real deal.
The real deal. These aren't just notes someone scribbled down. They're the distilled essence of critical knowledge. They're the very same tools pilots use day in, day out to master this aircraft.
So not just facts to memorize.
No, not at all. They're foundational elements for safe, efficient flight. They outline not just what to do, but they really imply the why behind every single critical step. You're looking at years of engineering, testing, real-world operational experience, all condensed down for immediate, flawless recall under pressure.
Wow.
It really shows you the absolute precision required, to ensure safety up there.
Okay, well, let's unpack this then and truly put our knowledge to the test. Are you ready? Let's see how well you'd navigate a high-stakes scenario in the Citation Sovereign. Let's begin. We're diving right into the heart of it, starting with the E-cards, that's emergency procedures. These are the immediate, almost rote actions that can make all the difference when the unexpected happens.
Seconds count here.
Absolutely. When the pressure is on, precision and speed here aren't just important. They are absolutely paramount.
You've hit on the core principle there. If we kind of connect this to the bigger picture, these memory items, they're designed to be almost reflexive, automatic.
Instinctive,
Yeah.
almost.
Exactly. They demand immediate action because they address the most critical threats first. This allows the crew to stabilize the aircraft before they can even think about diving into more detailed checklists.
Right. Stabilize first, then troubleshoot.
Precisely. And it raises an important question for any pilot, really. How deeply do we internalize these procedures before we're under the actual pressure of an emergency? The goal isn't just to know them, you see. It's to act automatically and correctly. Ensure the aircraft is safe before any further thinking can even begin. #TAG 1.1 fire and overtemperature scenarios.
Okay, let's start with a truly critical one. Scenario. You're operating on the ground, maybe getting ready for departure, could be taxiing, and suddenly you get an APU fire indication. What's your immediate memory item action? First thing.
Right. APU fire on the ground. Immediate action is direct and unambiguous. Push the APU fire button. That's it.
Simple, incredibly direct, and absolutely crucial. That button isn't just a light, it's an action trigger, isn't it?
It absolutely is. It initiates the fire suppression system, discharging a powerful extinguishing agent directly into the auxiliary power unit compartment.
So it hits the fire right where it starts.
Exactly. This rapid response is designed to contain a potentially catastrophic event, an APU fire, before it can spread to other vital systems or, the main fuel tanks. It's all about containing the threat the moment it's detected.
Makes sense. Okay, next scenario. You're cruising along nicely in flight, everything's normal, then you get a battery OTemp L or R message, an overheat warning for one of your main batteries. What's your primary response for the affected side?
Okay, for a battery OTemp L and or R, the immediate action is to select the battery T button affected side to O off F.
Okay, so you're effectively cutting off the power, trying to stop it from getting worse.
Precisely. You want to prevent further thermal runaway. Over temperature in an aircraft battery can lead to this uncontrolled chain reaction of heating, thermal runaway.
Which sounds bad.
It is bad. It can quickly degrade battery performance, severely damage other sensitive electrical components nearby, or, worst case, even lead to a fire. So disconnecting the affected battery immediately removes the heat source and isolates that unit from the rest of the aircraft. Well, pretty complex electrical system. Yeah. Stops the problem in its tracks.
Right, isolation is key. Okay, now, let's move to engine fires, obviously a major concern for any pilot. What's the procedure for an engine fire L and/or R when you're on takeoff, but specifically below V1 or if you're still on the ground?
Okay, that critical scenario on the ground or below V1, the immediate action for an engine fire is clear. Abort takeoff.
No hesitation there.
No.
Safety dictates an immediate abort. For our listeners, V1 or decision speed, that's the critical point during takeoff, right? Where a pilot has to decide continue or abort.
That's the moment of commitment, yeah.
So below V1, you've still got enough runway, hopefully, to safely stop the aircraft.
Exactly. Attempting to continue a takeoff with an engine fire at low speed or still on the ground just introduces unacceptable risks. The fire could escalate incredibly quickly, or you could get structural damage before the aircraft even reaches a safe flying speed. It's a definite stop-now moment.
Makes perfect sense. But how about if you're above V1 during takeoff? Or maybe you're already in flight at a safe altitude, say at or above 400 feet AGL, above ground level and conditions permit. Now you have an engine fire L and/or R. Yeah. Very different situation, right?
Indeed, yeah. This is a more involved, multi-step sequence. It reflects that shift from ground thinking to air thinking. First, you move the throttle, affected engine, to idly. Cut the fuel flow.
Okay, throttle idle.
Second, if your bleed air anti-ice is currently on, you need to select the anti-ice wing stab X-flow button to X-flow. Keep that anti-ice going from the good engine.
Right, maintain protection.
Then here's the key part. If the E-eng fire light is still illuminated after 15 seconds, then you push the illuminated E-eng fire button. And finally, you push either illuminated bottle armed button to discharge the extinguishing agent.
Okay, that 15-second delay is interesting. Why wait?
Well, what's truly insightful here is that delay. It's a calculated pause, really. A moment of waiting to see if simply cutting fuel to the engine by moving the throttle to idle might starve the fire.
Maybe it goes out on its own.
Possibly. Rather than immediately expending a valuable single-use resource, that fire bottle, it isn't hesitation. It's a strategic decision built right into the procedure to maximize your options under extreme pressure. If that light is still on after 15 seconds, well, that confirms an active, persistent fire, and then the extinguishing agent is deployed.
Got it. And the XFLW setting.
Right. The XFLOW for anti-ice ensures that essential wing and stabilizer anti-ice protection remains available, drawing bleed air from the good engine. This maintains critical flight safety, especially after an engine failure in icing conditions. It's a remarkable example of, well, really nuanced system design. Hashtag tag 1.2 cabin smoke management.
Okay, let's shift our focus a bit now to cabin integrity. What are the immediate memory item steps if you experience a cabin altitude emergency? This is where the environment inside the aircraft, the pressure, becomes compromised.
Okay, for a cabin altitude emergency, it's a critical three-part process, and it prioritizes life support above all else. First, oxygen masks on and 100%. Get oxygen flowing immediately.
Masks on first, always.
Always. Second, left and right, MIC/SL buttons to mask. Switch your comms to the mask microphone.
So you can talk to each other.
Right. And third, emergency descent as required. Get down to thicker air.
Getting oxygen is absolutely paramount before anything else in a situation like this, isn't it? A rapid decompression or just a sudden cabin altitude climb means the air pressure inside is dropping fast.
And that can quickly lead to hypoxia, a dangerous lack of oxygen for everyone on board.
Exactly. Donning those oxygen masks immediately ensures the crew remains conscious, capable, and clear-headed enough to actually fly the aircraft. That's always the first and most critical step.
Then switching comms to the mask allows for clear, unhindered crew coordination. And finally, that emergency descent aims to get the aircraft to a safer, lower altitude where supplemental oxygen might not even be necessary anymore. It's a sequence that literally prioritizes breathing first.
Okay. Now, smoke and odors in the cabin. Incredibly alarming for everyone, crew and passengers. What's the initial action for, say, environmental system smoke or odor or electrical system smoke or fire, or even just for general smoke removal? Are these procedures distinct, or is there a common immediate response?
Well, for all three of those scenarios, environmental system smoke or odor, electrical system smoke or fire, and general smoke removal, the immediate first step is actually consistent. Oxygen masks, goggles, don and emer.
Masks and goggles again. Priority one.
Priority one. This really highlights the overarching importance of protecting the crew from incapacitation, regardless of where the smoke is coming from. Smoke or toxic fumes, it doesn't matter the source, they can rapidly impair vision, cause severe respiratory distress, or even lead to unconsciousness very quickly.
Yeah, you don't have much time.
You don't. Donning masks and goggles provides immediate crucial protection. It allows the crew to see clearly and breathe safely while they work, to identify the source, and then execute further, more detailed checklist steps.
Right.
It does raise an important question about training, though. How quickly can pilots actually don and perfectly seal those masks in a real emergency, especially when they're already under immense stress?
Practice, practice, practice in the simulator, I assume.
Exactly. Simulator training focuses heavily on making this a swift, practice, almost instinctive motion. Hashtag tag 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 1.3 takeoff and engine malfunction management.
Okay, moving on to critical takeoff warnings. You're on the takeoff roll, accelerating, and you get a no takeoff message enunciated, and crucially, your speed is still below V1. What's the immediate call?
Speed below V1 with a no takeoff message means one thing definitively: take off abort. Stop the airplane.
Clear cut. And if that same no takeoff message appears when your speed is AT or above V1, now what?
In that case, the decision flips completely. You
Yeah.
climb to safe altitude, you're going flying.
That V1 point again. Such a critical moment.
It really is. This binary decision point at V1 is one of the most critical in all of aviation. It literally defines the gonna-go boundary. Below V1, like you said, you still have the runway length and the stopping capability to safely abort and bring the aircraft to a halt.
But above V1.
Above V1, however, the aircraft is committed to flight. Attempting to stop would likely result in a runway overrun, with potentially far more severe consequences than continuing the takeoff. So beyond V1, the safest option is almost always to continue the takeoff and deal with the issue airborne, where you're under controlled flight and, frankly, have more options.
Yeah, altitude gives you time.
It does. It's a moment of truth that every pilot trains for extensively.
That distinction is incredibly stark and important. Now, let's consider an engine failure or maybe some other emergency during takeoff. Again, with your speed below V1, what's the response there? Similar?
Yes, very similar to the no takeoff below V1. It's an immediate takeoff abort.
Okay. And if that engine failure or other emergency occurs AT or above V1,
Right.
what then?
Then you continue the takeoff. You climb to safe altitude, and again, if bleed air anti-ice systems are on, you would immediately select the anti-ice wing stab XLO button to XLO.
Right, that XL flow again. Making sure you're still getting anti-ice protection from the operating engine even after a failure.
Exactly. If one engine fails, the cross-flow system lets the remaining good engine provide bleed air for anti-ice to both wings and the horizontal stab. This maintains critical protection against ice accretion, which could otherwise really degrade your aerodynamic performance or lead to an unsafe flight condition pretty quickly. It's about leveraging every available resource to maintain safety.
Smart design. Now let's explore an uncommanded engine thrust situation. This means an engine is producing thrust without the pilot commanding it, a very serious malfunction. If this happens during takeoff below V1, what's the rapid sequence of actions?
Okay, this is a rapid, critical, two-step procedure. First, take off abort. Second, ENG fire button, affected side, push.
Whoa, push the fire button even without a fire. Explain that.
Yeah, what's truly eye-opening here is that immediate push of the ENG fire button, even without an actual fire. It's an emergency measure designed to completely shut down the engine and essentially regain control from that uncommanded thrust.
Ah, it's a shutdown switch in this context.
Exactly. Below V1, an uncontrolled thrust increase could make it absolutely impossible to stop on the remaining runway or even just maintain directional control. The fire button, in this context, serves as a direct, reliable, and swift engine shutdown mechanism. It prioritizes ground control and safety over any potential damage to an already malfunctioning engine. It's an extreme measure for an extreme situation.
Fascinating how a button designed for fire gets repurposed. Okay, what if that uncommanded engine thrust happens during takeoff above V1, or maybe during climb, cruise, or descent when you're already airborne?
In those airborne phases, the primary action shifts. It becomes climb to a safe altitude, if appropriate.
Different phase of flight, different immediate response really underscores how procedures adapt, doesn't it?
Absolutely. In these airborne phases, the priority shifts from stopping the aircraft on the ground to maintaining controlled flight in the air. Climbing to a safe altitude provides the crew with precious time and, well, physical space to analyze the situation, run the appropriate checklists, and safely manage the uncommanded thrust event without the immediate ground hazards you have during a low-speed takeoff or landing.
Okay, And what about during approach? You're preparing to land, getting configured, and you get an uncommanded engine thrust. What's your go-around procedure then?
Right. For uncommanded engine thrust, during approach, you would execute a go-around. This involves first, push the tow GA button, either throttle, that's takeoff go-around.
Initiate the go-around logic.
Yes. Second, advance throttles to TO, takeoff power. Third, set airplane pitch attitude to 7.5 degrees. Initially, following the flight director go-around command, then as required to establish a safe climb rate.
Got it. Apply power, pitch up, fly away.
Okay, finally, uncommanded engine thrust during the critical landing roll. How do you handle that? You're on the ground, maybe still at high speed. Right, you need to do two things quickly. First, maintain directional control. Use everything you've got: rudder, NWS, nose wheel steering, differential braking. Keep it on the runway.
Hold the center line.
Hold center line. And second, critically, push the ENG fire button affected side.
So again, the ENG fire button is quickly repurposed as a shutdown switch for uncommanded thrust, even on the ground during landing.
Correct. During the landing roll, uncommanded thrust makes it incredibly difficult, maybe impossible, to maintain the aircraft on the center line. It could lead to excessive speed and a runway excursion. By immediately shutting down the affected engine with that ENG fire button, the crew eliminates the uncontrollable thrust, allowing them to use other means, like differential braking, to bring the aircraft to a safe and controlled stop. It's a real testament to multifunctional emergency controls.
Okay, let's consider a dual-engine flameout. Both engines quit while you're in cruise flight. High altitude, high stakes. What's the very first thing you do?
For a dual-engine flameout while in cruise, the absolute first step, before anything else, is don crew oxygen masks, if required.
Protect the crew from hypoxia. Always priority one up high.
Absolutely. At cruise altitudes, FL 400 plus, even a brief interruption of pressurization or oxygen supply can rapidly lead to hypoxia. That severely impairs the crew's ability to respond to the emergency. Ensuring they are receiving adequate oxygen first maintains their cognitive function, keeps them sharp, and allows them to effectively execute the subsequent, often complex engine restart procedures. A clear mind is absolutely essential.
And what if a dual-engine flameout occurs at low altitude? Is the procedure different, given you have a much smaller safety margin, much less time?
Yes, at low altitude, the focus shifts because of that urgency. The procedure is, first, check fuel. Tank squad, is there fuel available?
Rule out the obvious first.
Exactly. Second, fuel boost buttons. Both on 10, get the pumps running. Third, throttles to cut off.
Why cut off?
Well, this sequence aims to rapidly determine fuel availability and prepare the fuel system for engine restart attempts. That's absolutely crucial when you have significantly less time to react due to being lower. There's less time to glide, less time to troubleshoot. Quickly assessing fuel status and priming the fuel boost system becomes paramount. Turning throttles to secute off also ensures the engines are in the proper commanded configuration for a restart attempt, preventing any residual fuel flow issues that could complicate the process.
Gotcha. Makes sense. What if you experience an engine failure during final approach? You're just moments from landing, configured, and suddenly an engine quits. What are your two immediate memory item actions?
You would immediately set flaps to 15 degrees and maintain an airspeed of VAPP, approach speed. Hashtag 1.4, control and flight dynamics emergencies.
Okay, now for a classic emergency that pilots train extensively for. You need to perform an emergency descent. What's the core directive? What's the main goal here?
The directive is simple and direct. Initiate maximum rate of descent to a safe altitude. Get down fast.
Maximum rate to get out of trouble quickly. How is that typically achieved?
Usually it involves reducing engine thrust to idle, extending the speed brakes to maximize drag, and increasing the aircraft's pitch-down attitude to achieve the highest safe vertical speed downwards, all while, crucially, maintaining positive control.
Right. Don't lose control while you're trying to get down.
Never. The goal is to quickly get to a lower altitude where a critical problem, maybe a pressurization failure or an uncontrollable fire, can be mitigated or safely managed without the added risks associated with high-altitude flight. It's all about speed and control.
Okay. What if you get an indication of thrust reverser unlock, or maybe an uncommanded deployment in flight, and the system indication is flashing? This implies a physical malfunction. What's the action you need to take immediately?
Okay, for that you would. First, push the TR-EMER stow button, the flashing button. Try to force it closed.
Have the stow button.
Second, set the throttle-affected engine to idle. Reduce the thrust involved. Third, reduce airspeed to 150 kS maximum. slow down to reduce aerodynamic forces.
Right. This is all about immediately trying to restow the reverser and reducing airspeed to minimize the effects, like aerodynamic drag and control issues that come from an open, uncommanded reverser.
Exactly. An unexpected thrust reverser deployment in flight can cause significant asymmetric drag, potentially leading to severe control difficulties, especially at higher airspeeds. The emergency stow button attempts to lock the reverser back into its safe, stowed position, and reducing throttle and airspeed lessens the aerodynamic forces acting on that deployed reverser, helping the pilot regain control and prevent further structural damage. It's really a race against those aerodynamic forces.
Let's talk about trim runaways. This is when the aircraft's trim surfaces pitch, roll, or rudder trim start moving on their own without pilot input. Can be very disorienting. What's the action for a primary pitch trim runaway, an aileron trim runaway, or a rudder trim runaway?
Okay, for any of those primary trim runaways, primary pitch trim runaway, aileron trim runaway, or rudder trim runaway, the response is the same, thanks to a pretty brilliant design principle. Push and hold the APTRIM NWS Disky button, the big red button on the yoke.
Ah, the master disconnect. That single multi-purpose button is designed to disconnect multiple systems simultaneously, right? Giving you a quick, decisive way to regain control.
Precisely. A trim runaway means the trim surfaces are moving without your input, creating unwanted pitch, roll, or yaw. This can very rapidly make the aircraft difficult, if not impossible, to control manually. The ATRIM and NWS Disky button is essentially a master kill switch for those systems. It cuts power to these potentially malfunctioning systems and allows the pilot to regain full manual control and neutralize the runaway condition. It's quite an elegant solution for a complex problem under pressure.
What about a secondary pitch trim runaway? Is the procedure different? Does that imply a separate system?
Yes, it is different, and yes, it implies a separate system. For a secondary pitch trim runaway, you specifically select the secondary trim button to off. There's a dedicated switch for it.
Okay, so that highlights a dedicated control for the secondary system, separate from the primary trim and autopilot disconnect button.
Exactly. It implies a design where the secondary system has its own distinct electrical circuit and control, allowing for a more isolated and specific response compared to the broader disconnect used for primary trim issues. It's a subtle but important layer of redundancy.
Now for a more complex and, frankly, potentially terrifying scenario. A jammed pitch or roll control system. One of your primary flight controls, the yoke or stick, is physically stuck. What's the recovery sequence for this?
Okay, this involves several critical steps, and it requires coordination. First, actuate the stabilizer trim switch to establish desired pitch attitude. Use trim to control pitch if the elevator is jammed.
Fly with trim.
Fly with trim. Second, relax pressure on the control wheel. Don't fight the jam unnecessarily. Third, pull the pitch roll reconnect handle until latched. This is the key step.
The reconnect handle. Explain that.
Right. Fourth step is identify the operative flight control wheel, the one that isn't jammed, and use it to recover airplane attitude. That pitch roll reconnect handle is a unique and incredibly important feature in this aircraft. It allows one pilot to essentially disconnect their jammed controls from the other pilot's controls.
So one pilot can fly even if the other's controls are stuck?
Exactly. If one pilot's control column or yoke becomes physically jammed, this system allows the other pilot to isolate the jammed side and gain full, unhindered control of their side, ensuring that the aircraft can still be flown safely. It's a critical safety redundancy designed to overcome a severe mechanical malfunction that would otherwise likely be catastrophic.
Wow. Okay. What are the immediate actions for an inadvertent stall? Let's say it's indicated by the stick shaker activating, maybe some airframe buffet, and a door and uncontrolled roll-off.
Okay, for an inadvertent stall, you would?
Yeah.
First, push the APTRI MWS DSE button. Disconnect automation.
Get manual control.
Yes. Second, reduce pitch attitude. Lower the nose to decrease the angle of attack. Third, level wings for roll attitude. Use ailerons to stop any roll. Fourth, advance throttles to TO detent. Apply maximum available power.
That sounds like the classic textbook stall recovery procedure, doesn't it?
It is. Reduce the angle of attack, add power, and maintain control. A stall occurs when the wing's angle of attack exceeds its critical point, leading to a sudden loss of lift. These immediate actions are precisely designed to decrease that angle of attack, restore smooth airflow over the wings by adding power, and prevent uncontrolled rolling, thereby regaining lift and stable flight as quickly and safely as possible.
And pushing the DISC button first.
Right. That ensures that the autopilot or any potential runaway trim isn't fighting your recovery inputs, which could seriously hinder or even prevent the recovery.
Makes sense. Okay, the dreaded WinJ, that's wind shear message, appears in the right PFD, primary flight display. This is a very dangerous weather phenomenon, especially low to the ground. What are your three immediate memory item actions?
Okay, for a wind shear warning, first, advance throttles to toe to 10, max power.
Power up.
Second, set pitch attitude to go-around attitude, 7.5 degrees. Pitch for climb performance, following the flight director it's available. Third, ensure the speed brake handle is at 0%, fully stowed. Minimize drag.
These actions are all about maximizing climb performance to escape the wind shear, right? Get away from the ground.
Absolutely. Wind shear is a sudden, drastic change in wind speed or direction over a very short distance. It can cause rapid and dangerous losses or gains in airspeed and altitude, making it particularly hazardous during takeoff or landing. These three actions collectively aim to maximize engine thrust and climb capability while simultaneously minimizing aerodynamic drag. This provides the best possible chance to fly through or climb out of the wind shear conditions safely. It's a full-power climb-away maneuver. Hashtag 1.5 braking system emergencies.
Okay, last one in this emergency section. During landing, you experience a hydraulic wheel brake failure. Your primary brakes are gone. What's your immediate response in that critical moment on the runway?
Okay, brake failure on landing. First, immediately remove feet from brake pedals. Get off the failed system.
Feet off the pedals.
Then, pull and hold the emergency brake handle
Yeah.
until stopped. Engage the backup system.
So this immediate sequence bypasses the failed hydraulic system and applies the emergency braking, which typically operates independently, right?
Correct. It raises an important question for pilots, though. What's the tangible difference in feel and effectiveness between normal braking and emergency braking? The emergency brake system often operates mechanically or perhaps with a separate hydraulic accumulator. It might not offer the same modulated, nuanced control as the main system. It might be more abrupt, maybe less powerful overall.
And removing your feet from the pedals first.
That prevents any residual pressure from the failed main system or even just your own inputs on the failed pedals from interfering with the emergency brake's operation. It ensures its full, undiluted effectiveness when you absolutely need it most to stop the airplane.
All right, we've covered the E cards, those critical emergency actions where seconds count. Now we're moving on to the L cards limitations. These aren't about immediate crisis management in the same way. Instead, they define the very boundaries, the envelope within which this aircraft can safely operate.
Yeah, these are the hard lines you just don't cross.
Exactly. Ignoring these isn't just a recommendation, it can lead to very serious trouble.
Absolutely. If we connect this to the bigger picture again, these limitations are completely non-negotiable. They aren't suggestions. They're derived from extensive flight testing, detailed engineering analysis, and rigorous certification processes by the authorities. They represent the absolute edge of the aircraft's performance and its structural integrity.
So they define the safe operating envelope.
Precisely. And a deep understanding of them helps pilots make proactive, safe decisions before things go wrong, rather than just having reactive responses to problems after they happen. These aren't suggestions. They are hard, regulatory limits set by the manufacturer and the certifying bodies like the FAA or EASA. They're there to ensure the aircraft remains structurally sound, predictable, and safe under all anticipated conditions.
And they impact everything, right? Flight planning, fuel loads.
Everything. Fuel load planning, route selection, takeoff and landing performance calculations, speed management, you name it. Hashtag 2.1 weight and fuel.
Okay, let's start with some absolutely foundational numbers, the real building blocks of flight planning. What are the maximum design ramp weight, maximum design takeoff weight, maximum design landing weight, maximum design zero fuel weight, the minimum flight weight, and the maximum tail tone baggage weight for the Citation Sovereign? Give us the key figures.
Okay, the key weight limits are maximum design ramp weight, that's 30,550 pounds, just slightly more than takeoff weight to allow for taxi fuel burn. Maximum design takeoff weight is 30,300 pounds. Maximum design landing weight is significantly lower, 27,100 pounds. Maximum design zero fuel weight, which is the max weight of the aircraft before you add any usable fuel, is 20,800 pounds.
Important for structural limits.
Very. Minimum flight weight is 17,345 pounds, and the maximum tail cone baggage weight is 1,000 pounds.
These numbers are absolutely foundational for any flight planning, truly crucial for calculating performance, weight, and balance.
Couldn't agree more. For our listeners, exceeding any of these limits could severely compromise the aircraft's structural integrity, maybe its control authority, or its performance characteristics during different phases of flight, from just sitting on the ramp to the moment of landing touchdown.
Yeah, you really have to respect these numbers.
Absolutely. Pilots use these figures for incredibly precise weight and balance calculations before every single flight. These calculations directly influence everything from takeoff and landing distances required to climb rates, cruise speed, fuel burn, and ultimately overall flight safety. It's not just a number on a page, it's a hard physical boundary determined by physics and engineering.
Okay. How do we define unusable fuel for the Sovereign? What does that term actually mean in practical terms?
Unusable fuel is precisely defined as the fuel remaining in the fuel tanks when the fuel quantity indicator reads 0. This fuel is, by its very definition, not usable in flight by the engines. You gotta count on it.
So even when the gauges say empty, there's still a bit left. Why?
Yeah, it raises an interesting design point. Why is there unusable fuel, and what factors contribute to it? It's often due to the physical shape of the fuel tanks, the precise location of the fuel pump pickup points within those tanks, and also the aircraft's varying attitude during different phases of flight, climb, descent, turns.
So some fuel just gets trapped.
Essentially, yes. Even when the gauges read empty, a small amount of fuel remains simply because it cannot be reliably scavenged or pumped to the engines under all conditions. This amount is carefully calculated and accounted for in all fuel planning calculations, and critically, it should never be considered part of the usable fuel available for a flight. It's a built-in safety buffer, really. Hashtag 2.2 takeoff and landing operational limits.
Okay, let's talk about the operational edges for takeoff and landing. What are the maximum altitude limit for takeoff and landing? What's the maximum tailwind component permitted? And what's the maximum demonstrated crosswind component? Noting that last one is often listed as not limiting.
Right. The maximum altitude limit for takeoff and landing is 14,000 feet pressure altitude. The maximum tailwind component allowed is 10 knots. And the maximum demonstrated crosswind component, while technically not a regulatory limit, is 25 knots.
Okay, 14,000 feet for takeoff or landing is quite high. Think about places like Telluride or Leadville. But it's a definitive hard limit for this aircraft's performance certification.
Yeah, engine and wing performance drop off significantly at those altitudes.
And those tailwind and crosswind components are equally critical for safe operations, aren't they? Particularly during the high-demand phases of takeoff and landing.
Absolutely. Exceeding a tailwind limit can significantly increase your required takeoff and landing distances because the aircraft needs more ground speed to achieve its flying speed. Conversely, an excessive crosswind can make maintaining directional control extremely challenging, risking a side load on the gear, a runway excursion, or just placing undue structural stress on the landing gear itself. Pilots have to be acutely aware of these environmental factors and adjust accordingly.
Definitely. What's a critical system status requirement for takeoff and landing, specifically regarding the autopilot and the yaw damper? Can you use them?
No, it's a non-negotiable requirement. The autopilot and yaw damper must be disengaged for both takeoff and landing.
So, even in such a modern, highly automated aircraft, the human pilot is absolutely expected to be in direct manual control during these most critical phases of flight. Why is that?
Well, it's fascinating, isn't it? While autopilots are incredibly sophisticated and reliable, the dynamic and rapidly changing conditions during takeoff and landing, think gusts, wind shear, the need for precise flare control, really require the immediate, nuanced responses and acute situational awareness that, frankly, only a human pilot can provide reliably in every situation.
The feel of the aircraft.
Exactly. Disengaging these systems ensures the pilot has full manual control and that direct feel of the aircraft, which is pretty irreplaceable during those moments.
Okay. Can you list the systems that require a satisfactory pre-flight check prior to takeoff? According to the normal procedure section, these are the absolute must checks before you go.
Sure. A satisfactory pre-flight check is required for the angle of attack and stall warning systems, the bleed air system, the glare shield cooling fans, the rudder bias system, standby power, and the stabilizer trim system.
Got it. Quite a list. Let's talk about cabin configuration and runway conditions for takeoff and landing. How must the lavatory doors be latched? What type of runway surfaces are permitted? And must anti-skid be operational?
Okay, 3 things there. The lavatory doors must be latched open for takeoff and landing. Takeoffs and landings are strictly limited to paved runway surfaces only. And yes, the anti-skid system must be operational for takeoff.
Okay, latched open lav doors might seem like a small detail, but why is that a requirement?
It's a critical safety measure, actually. It prevents them from potentially jamming shut in an emergency, like a hard landing or rejected takeoff. It also ensures that emergency egress routes remain clear and allows flight attendants or crew to quickly access the entire cabin if needed during those critical phases.
Makes sense. And paved runways.
Expected for this class of aircraft due to their weight, tire pressure, and susceptibility to foreign object debris, FOD ingestion, unpaved surfaces can cause damage or increase risks significantly.
And anti-skid must be working for takeoff. Crucial for ejected takeoffs, right?
Absolutely vital for maximizing braking effectiveness and maintaining directional control during high-speed ground operations, especially if you have to abort the takeoff. Every detail is carefully considered for safety.
Okay. When must speed brakes be stowed prior to landing? Unless the aircraft's flight manual specifically allows otherwise.
Speed brakes must be stowed prior to 500 feet AGL above ground level for landing. You need to be in a stable landing configuration by then.
Right. What type of caution and warning messages, when displayed on the IISIS, specifically prohibit takeoff? And related to de-icing, what is the flap configuration limit when Type 2, 3, or 4 anti-ice fluid has been applied to the aircraft?
Okay, takeoff is absolutely prohibited with any red message displayed. Takeoff is also prohibited with an amber message displayed unless specific relief is authorized in an approved minimum equipment list, MEL, for that aircraft.
So red means stop, amber means maybe. Check the mail.
Essentially, yes.
Yeah.
And regarding anti-ice fluid, takeoff is limited to the flap's 7-degree configuration only when Type 2, 3, or 4 anti-ice fluid has been applied.
Why the specific flap setting?
Well, this distinction between red and amber messages is a key operational concept. Red typically indicates an immediate safety of flight issue needing action or grounding the plane. Amber denotes an abnormal condition that might allow dispatch under very specific MEL conditions and procedures. The specific flap setting of 7 degrees, when those thicker anti-ice fluids are applied, is crucial. Type 2, 3, and 4 fluids are viscous and can actually affect the aerodynamics of the wing, potentially changing its stall characteristics or performance. This limitation mitigates any potential performance degradation and ensures the wing performs predictably during the critical takeoff phase. Hashtag 2.3 and read operational limits.
Okay, let's talk about getting up high. What is the maximum operating altitude for the Sovereign? And are there specific conditions that must be met for operations above FL 410, that's flight level 410, or 41,000 feet?
The maximum operating altitude is 47,000 feet, FL 470. And yes, for operations above FL 410, specific conditions apply. Both ENG BLD air selectors must be selected to norm or HP, and critically, both engine bleed air sources must be available and functioning. Additionally, the press source selector must be selected to norm.
FL 470, that's really up there in the thin air. These conditions seem focused on ensuring adequate pressurization and anti-ice capability, right?
Absolutely. Operating at such extreme altitudes places significant demands on the aircraft's environmental and anti-ice systems. Requiring both engine bleed air sources to be available and selected correctly ensures that the cabin remains safely pressurized, preventing hypoxia. It also guarantees that critical anti-ice systems have a sufficient supply of hot bleed air to function effectively, maintaining a safe environment for occupants and reliable aircraft performance in those very thin, very cold atmospheric conditions.
Makes sense. What's the maximum altitude with flaps extended? Can you fly high with flaps out? And what is the requirement for the Mach trim system for speeds above Mach 0.77, specifically when the autopilot is disengaged?
No, you can't fly high with flaps out. The maximum altitude with flaps extended is 18,000 feet. And regarding Mach trim, the Mach trim system must be operational for speeds above Mach 0.77 with the autopilot disengaged.
Okay, so 18,000 feet for flaps, that seems reasonable. But the Mach trim requirement above 0.77 without the autopilot, that really highlights its importance at higher speeds, doesn't it?
It really does. Extending flaps at high altitude leads to excessive drag and potential structural stress, hence the 18,000-foot limit. The Mach trim system is crucial for maintaining longitudinal stability, basically pitch stability, at high Mach numbers. It automatically adjusts the horizontal stabilizer trim to counteract aerodynamic changes in the center of pressure that occur as the aircraft approaches the speed of sound. These changes can make the aircraft feel unstable or difficult to control manually.
So if the autopilot isn't active to manage this automatically,
Then the manual Mach trim system must be fully functional to provide that essential stability assist to the pilot. It's a critical safety system for high-speed flight. Hashtag 2.4 power plant and engine operations.
all right, let's get into the heart of the aircraft, its engines. What is the specific engine type used on the Sovereign, and what is its impressive thrust output at sea level up to 30 degrees C ISA conditions?
The engine type is the Pratt & Whitney Canada Inc. PW306E turbofan, a very reliable engine, and it produces a robust 5,770 pounds thrust per engine at sea level up to 30 degrees C.
Okay. What's the limit for continuous static ground operation of the engine at takeoff thrust? Can you just sit there holding the brakes at full power indefinitely? And when is an engine start specifically prohibited due to tailwind conditions?
No, you definitely can't hold takeoff thrust indefinitely on the ground. Continuous static ground operation at takeoff thrust is limited to a maximum of 2 minutes, and attempting an engine start is prohibited with a tailwind component greater than 10 knots.
Why those limits? 2 minutes seems short, and why worry about a tailwind during start?
Well, 2 minutes at full power on the ground generates an immense amount of heat and stress on those engines. Running engines at takeoff thrust for extended periods on the ground significantly increases component wear and tear, especially due to the very high exhaust gas temperatures, EGT, and stresses on the engine core and turbine sections. It's just hard on the engine.
Okay, heat management and the tailwind.
The tailwind limit is primarily to prevent what we call hot starts or potentially compressor stalls. A strong tailwind can effectively reduce the airflow into the engine during the start sequence. This can lead to excessive internal temperatures, a hot start, or an uneven airflow through the compressor stages, which can cause a compressor stall. Both of these conditions can severely damage the engine, so limiting starts with the tailwind is a critical protective measure.
Got it. Regarding engine oils, what is the maximum oil consumption rate allowed for the Sovereign, and what's the strict rule about mixing different oil types or brands? Can you just top it off with whatever's handy?
No, definitely not. Maximum oil consumption is limited to 1 quart per 8 flight hours. And critically, oil types or brands may not be mixed unless it's specifically approved in the PW306C maintenance manuals. You have to use the approved type.
Consistency in oil type is really critical for engine longevity, isn't it?
Absolutely. Exceeding that oil consumption rate usually indicates a potential internal engine issue, maybe a seal leak or something more serious. That absolutely requires maintenance investigation. And mixing different oil types or brands, even if they seem similar, can lead to chemical incompatibilities. This might cause foaming, reduce lubrication properties, or sludge formation, all of which can cause significant internal engine damage over time. Adhering to these strict guidelines ensures the engine's complex internal components are properly lubricated and cooled, maintaining their integrity and reliability.
Okay. Let's review the engine operating time limits for different power settings. What are they for takeoff, and note the difference between two engines operating versus only one engine? What about maximum continuous, MCT, maximum cruise, CRU, and reverse thrust?
Okay, the time limits are, for takeoff power, it's 5 minutes when using 2 engines, but you get an extended allowance of 10 minutes when operating on only one engine.
Ah, interesting difference there.
It is. For maximum continuous MCT and maximum cruise, CRU, the limit is continuous. You can run at those settings indefinitely, theoretically, and reverse thrust is limited to 5 minutes of use.
That longer limit for single-engine takeoff power makes sense, giving you more time in an emergency.
Exactly. It's a key safety feature. It provides the pilot with more time to achieve a safe altitude, clean up the aircraft configuration, and get established in an engine-out emergency after V1, acknowledging the increased demand and stress on the remaining operating engine. The continuous operation limits for MCT and CRU reflect their design points for sustained flight phases. And the reverse thrust limit is usually due to the stress and heat generated by the reverser mechanism itself, not necessarily the engine core.
Okay, let's talk temperatures. What are the maximum observed ITT degrees interstage turbine temperature limits for takeoff, maximum continuous, maximum cruise, reverse thrust, starting, and transient conditions, which is defined as 20 seconds?
All right, the ITT limits are, for takeoff, maximum continuous, maximum cruise, and reverse thrust, the limit is all the same, 920 degrees C. However, for starting and for transient conditions, up to 20 seconds, there's a slightly higher allowance of 950 degrees C.
Those temperature limits are obviously crucial to prevent melting expensive parts of the engine.
Absolutely crucial. They prevent engine damage. The interstage turbine temperature, ITT, is one of the most critical indicators of engine health, directly reflecting the thermal stress on the turbine blades, which are working in an incredibly hostile environment. Exceeding these limits, even briefly, can lead to permanent damage to hot section components, things like blade stretching or cracking, severely compromising engine reliability, and potentially leading to a catastrophic failure down the road.
And the slightly higher allowance for starting and transient.
That accounts for the temporary, predictable thermal spikes that naturally occur during these dynamic phases of engine operation, like light off during start or rapid power changes. The engine can tolerate slightly higher temps for very brief periods. Hashtag tag 2.5 start cycle limits.
Okay, moving on to engine starting protocols and limits. What are the specific required rest periods between engine start attempts? You can't just keep cranking the starter if it doesn't light off, right?
No, definitely not. You need to let things cool down. The required rest periods are 2 minutes of cooling after the first start attempt. If you need a second attempt, you wait 5 minutes after that one. And if you need a third attempt, you have to wait a full 30 minutes after that before trying again.
Why these specific increasing rest periods?
These rest periods are primarily designed to allow critical components, especially the starter motor and associated electrical wiring and batteries, to cool down. They also allow the aircraft's batteries to recover some charge. The starter motor generates significant heat during a start attempt. Allowing adequate cool-down time prevents overheating and premature wear, extending the life of these expensive components. Plus, giving the batteries time to recover ensures you have sufficient power for any subsequent start attempts. It's all about protecting the equipment and ensuring you have the capability for the next try.
Makes sense. What about engine starter motoring limits? This is when you're just spinning the engine with the starter, maybe for clearing fuel or cooling, not actually trying to start it. What are the time limits for motoring using batteries only, using batteries with generator assist from the other engine, using external power at 1,000 amps, and using external power at 1,500 amps? These seem to vary quite a bit.
They do vary depending on the power source. For motoring on batteries only, 20 seconds maximum continuous motoring. For batteries with generator assist, 15 seconds. For external power at 1,000 amps, also 15 seconds. And for the high-power external power card at 1,500 amps, a very short 7 seconds.
Wow, only 7 seconds with the 1,500 amp cart. Why the shorter limit with higher current external power seems counterintuitive.
It does seem a bit counterintuitive, but it raises an important point. It's primarily due to the increased thermal stress on the starter motor itself. While higher power sources can spin the engine faster, they also deliver significantly more electrical current through the starter windings, generating heat much more rapidly.
So more power means faster heating.
Exactly. This requires shorter operating times, motoring times, to prevent damage to the starter motor from overheating. These limits are precisely calibrated based on testing to protect the starter motor from thermal damage and premature failure. It's a core component for getting your engines running, so you have to treat it right.
Okay. What are the APU starter limits in terms of start cycles and rest periods? And what are the general battery start limits for both the main engines and the APU, typically measured per hour?
Okay, for the APU starter limit, you are allowed 3 APU start cycles per 30 minutes. And you need a mandatory 90-second rest period between each of those cycles.
3 starts per half hour, 90 seconds rest. Got it.
For the general battery start limit, considering the load on the main aircraft batteries, it's 3 engine starts per hour using battery power and 9 APU start cycles per hour, again, using battery power.
Now, for some slightly complex equivalencies, which seem crucial for managing battery life and preventing battery damage, how many engine external power starts, when the available current is greater than or equal to 1,000 amps, are considered equivalent to 1 engine battery start? What about 1 external power start when the current is less than 1,000 amps? What about 3 generator-assisted cross starts? And finally, how many APU battery starts equal 1 engine battery start in terms of battery drain?
Okay, these equivalencies help track cumulative battery usage. Here they are. 3 engine external power starts, using a strong external power source, or 1,000 amps, are equivalent to 1 engine battery start.
So external power is much easier on the battery.
Generally, yes, especially high amperage cards. However, 1 engine external power start, using a weaker external power source, 1,000 amps, is considered equivalent to 1 engine battery start.
So weaker carts don't save the battery as much.
Correct. 3 generator-assisted cross starts, using the running engine's generator to help start the other, are equivalent to 1 engine battery start. And finally, 3 APU battery starts are also considered equivalent to 1 engine battery start.
These equivalencies seem absolutely critical for managing battery life, especially in remote locations, and preventing overstressing the electrical system during multiple start attempts, whether it's for training or maintenance or just trying to get going.
They really are. They provide a practical guideline for pilots and maintenance crews to understand the cumulative electrical load and heat stress on the aircraft's batteries and starting systems. For example, knowing that 3 APU starts equate to 1 engine start helps a pilot decide whether to conserve precious battery power for potential critical engine restarts later, or maybe use the APU more freely if ground power isn't available. It's all about smart resource management based on the aircraft's limitations.
Okay, what are the maximum current and voltage limits for the external power source itself when starting the aircraft?
The maximum current allowed from the external power unit is 1,500 amps, and the maximum voltage is 28 VDC. volts direct current. Hashtag 2.6 speed limits.
All right, let's dive into the speed envelope, V-speeds, and Mach limits. What is the maximum operating Mach number, MMO, permitted above 29,833 feet? What about the maximum operating speed in knots, VMO, between 8,000 feet and 29,833 feet? And what is VMO below 8,000 feet?
Okay, the speed limits change with altitude. Above 29,833 feet, the limit is expressed in Mach number. MMO is Mach 0.80 indicated. Between 8,000 feet and 29,833 feet, the limit is VMO, which is 305 knots indicated airspeed. And below 8,000 feet, VMO reduces to 270 kias.
These numbers define the crucial speed envelope at different altitudes, a fundamental part of flight planning and, obviously, flight execution.
Absolutely. MMO, maximum Mach operating, and VMO, maximum operating speed in knots, are critical aerodynamic limitations that the aircraft must not exceed. Flying faster than these limits can lead to structural damage due to excessive air loads or adverse aerodynamic effects like Mach buffet, where the airflow over the wing becomes turbulent and lift is disrupted at high speeds, or even a loss of control effectiveness.
So these are hard limits based on testing.
Extremely hard limits. They are meticulously determined during extensive flight testing to ensure the aircraft remains safely within its design capabilities across all the varying altitudes and atmospheric conditions it might encounter. It's a key part of staying within the certified design limitations.
Okay, what are the maximum flap extended speeds, VFE, for the different flap settings? The 7-degree position, the 15-degree position, and full flaps, which is the 35-degree position. These are speeds you absolutely cannot exceed with those flaps deployed.
Right, the VFE limits are for partial flaps, 7-degree position, the limit is 250 ks. For the 15-degree position, it drops to 200 ks. And for full flaps, 35-degree position, it's 175 ks.
And what about the landing gear? What is the maximum landing gear operating speed, VLO, which is the speed you can extend or retract it, and the maximum landing gear extended speed, VLO, the speed you can fly with it down? Are they the same on the Saturn?
Yes, they are the same for this aircraft. VLO is 210 ks.
Exceeding these speeds seems like a really bad idea, potentially causing serious structural damage to the flaps or the landing gear.
Definitely a bad idea. Flaps are specifically designed to be extended at lower airspeeds to increase both lift and drag, primarily for takeoff and landing phases. Deploying them at too high an airspeed can critically overstress their structure. The tracks, the actuators, the flap surfaces themselves, potentially leading to failure. Similarly, the landing gear mechanism, the doors, and the gear structure are not designed to withstand the immense aerodynamic forces encountered during deployment or extended flight at excessive speeds. You risk damage, failure to retract, or even separation of gear components. It's all about respecting the physical limits of these moving parts under air load.
Makes sense. What's the maximum turbulent air penetration speed, the recommended speed for flying through rough air? What about the speed brake extension speed? Is there a limit? What's the minimum speed brake extended speed, specifically for 10 panels deployed? And what's the recommended single-engine en route climb speed?
Okay, several speeds there. Maximum turbulent air penetration speed is 225 kis, or Mach 0.73, whichever is lower at your current altitude.
So a defined speed for turbulence.
Yes. Speed brake extension speed has no limit. You can deploy them at any speed within the aircraft's normal operating envelope, which is quite flexible.
Interesting. But there's a minimum speed.
Yes, the minimum speed brake extended speed with 10 panels, which is full deployment, is VREF plus 15 ks. VRF being your landing reference speed. You need to stay above that to maintain adequate control margin. And finally, the recommended single-engine en route climb speed is 180 ks.
Okay, the no limit for speed brake extension is interesting, shows they're built strong. But that minimum extended speed is key for maintaining control authority, especially when you've got all that drag hanging out.
Exactly. Turbulent air penetration speed is specifically calculated to provide the safest airspeed for flight in moderate to severe turbulence. It balances the need to slow down to reduce structural loads from gusts against the need to maintain adequate control response and stay well above stall speed. The minimum speed brake extended speed ensures that even with significant drag, the aircraft maintains sufficient control authority and remains safely above stall margin, which is particularly important if you're using them during an approach.
And the single-engine climb speed.
That 180 ks is optimized to achieve the best rate of climb performance after an engine failure during the en route phase, balancing airspeed needed for cooling and lift with the reduced thrust available from the single operating engine.
Got it. Last couple of speeds. What is the maximum tire ground speed for the Citation Sovereign, and what's the minimum speed for sustained flight in icing conditions, specifically excluding takeoff, approach, and landing phases?
The maximum tire ground speed is 165 knots, and the minimum speed for sustained flight in icing conditions, outside of takeoff, approach, landing, is 180 kis. Hashtag 2.7 APU in electrical systems.
Okay, let's shift to the auxiliary power unit, APU, and the electrical system limits. Let's review the engine generator and APU generator limits. What are the amperage limits for each on the ground, in the air generally, and specifically for operations above 35,000 feet?
Right. The generator load limits vary. On the ground, the engine generator limit is 300 amps, and the APU generator limit is 275 amps. In the air, below 35,000 feet, the engine generator limit remains 300 amps, and the APU generator limit is also 275 amps. However, above 35,000 feet, the engine generator limit drops to 275 amps, and importantly, the APU generator limit becomes NA, not applicable.
NA, so the APU cannot be used as an electrical generator above 35,000 feet.
Correct. It might still run for bleed air up to its operating limit, but it can't provide electrical power that high.
That drop in the engine generator limit at high altitude and the APU not being available as a generator above FL 350 are indeed very important distinctions for pilots to be aware of, especially during electrical planning or emergencies.
Absolutely. These limits primarily reflect the cooling capabilities of the generators themselves at different ambient air densities and temperatures. At higher altitudes, the thinner air provides less effective cooling for the electrical components, necessitating a reduced output limit for the engine generators to prevent them from overheating. The APU's operational envelope is also inherently limited by altitude. It simply cannot reliably generate electrical power or sometimes even operate at all above certain flight levels due to insufficient air density for combustion and cooling. It's a classic example of environmental factors dictating crucial operational limits.
Makes sense. What about the APU's operating envelope itself? What's its maximum altitude for starts? Its maximum airspeed for starts, its maximum operating altitude for bleed air, and its maximum operating airspeed. Also, crucially, after a dual generator failure, a major electrical emergency, how many APU start attempts are permitted?
Okay, the APU envelope. Maximum altitude for APU starts is FL 200, flight level 200, or 20,000 feet. Maximum airspeed for APU starts is 250 kis. The maximum operating altitude for the APU providing bleed air is FL 300. The maximum operating airspeed for the APU is 305 kis, or Mach 0.80, whichever is controlling. And importantly, after a dual generator failure, only one APU start attempt is permitted on battery power alone.
Only one attempt after losing both generators. Wow.
Yes, that highlights the need to conserve battery power.
These numbers indicate a pretty significant operating envelope for the APU overall, but also very strict boundaries, especially that single start attempt rule.
They do. The APU provides an independent source of electrical power within its limits and bleed air, which is absolutely crucial for ground operations, air conditioning, engine starting, and serves as a vital backup in flight for certain systems and restarts. Its operational limits are precisely governed by its physical ability to reliably start, operate, and cool itself within varying atmospheric conditions, altitude, and airspeed. That single start attempt after a dual generator failure underscores the absolute criticality of battery conservation in a severe electrical emergency. The APU might be your only hope for restoring significant power, so you get one shot to start it before the batteries potentially deplete too far. It's a very deliberate design consideration to manage precious resources under extreme duress.
Okay. After an APU shutdown, how long must you wait before attempting a restart? Is applying de-ice or anti-ice fluid permitted while the APU is operating? Is unattended operation of the APU allowed on the ground? And what specific action must happen after an automatic APU shutdown occurs?
Right, some procedural limits here. Following an APU shutdown, a restart must not be attempted until 30 seconds after the APU RPM indicator reads 0%. Let it spool down completely and cool slightly.
30 seconds after 0 RPM. Got it.
Applying de-icy anti-ice fluid of any type is prohibited when the APU is operating. You don't want that stuff ingested.
Makes sense. Keep fluids away from the intake.
Unattended operation of the APU is prohibited. Someone needs to be monitoring it. And crucially, the APU compartment must be inspected by maintenance following any automatic shutdown.
Why these specific rules? They seem geared toward safety and preventing damage.
They absolutely are. They're critical safety measures. The 30-second waiting period after shutdown allows the APU's internal components, especially the hot section, to cool down slightly and ensures any residual fuel vapors have dissipated, significantly reducing the risk of a damaging hot start on the next attempt. Prohibiting de-icy ice fluid application while the APU is running prevents the ingestion of potentially corrosive or flammable liquids into the APU air intake or exhaust. Unattended operation is a fundamental safety precaution to ensure immediate human response in case of an APU fire or other malfunction. And that inspection after an automatic shutdown is absolutely crucial to identify and rectify the underlying cause. An auto shutdown indicates a problem, maybe overheating, oil pressure loss, or something else that needs to be fixed before relying on the APU again. It's all about preventing a small issue from escalating into a major incident.
Okay. Is operating the cockpit and cabin temperature controls in manual permitted while the APU max cool function is selected on clap? And if it's not permitted, what's the required waiting period after selecting APU max cool to off-F before you can use manual temperature controls?
Right, that's a specific interaction. Operating the cockpit and cabin temperature controls in manual mode is prohibited while APU max cool is selected on N. You have to let the automated system run. And if you turn max cool off, a 30-second waiting period is required after selecting APU max cool to off-F before you can operate the cockpit and cabin temperature controls in manual mode. Hashtag 2.8 FADC in hydraulic systems.
Okay, let's discuss the FADC system, the full authority digital engine control. This is basically the engine's computer brain. Is dispatch permitted with an engine FADT channel inoperative? What about exceeding the time interval specified for a cyan engine dispatch limit message? And what's the requirement regarding the air data systems for dispatch?
Okay, FADC limits are strict. Dispatch with an engine dispatch limit L is absolutely prohibited. You need both channels operational. Exceeding the time interval allowed for a cyan engine dispatch limit L and door arm message is also prohibited. You have a limited time window to fix the issue indicated by that message. And critically, both air data systems must be operational for dispatch.
FADC is so critical for modern engine management, it makes sense. These are very strict dispatch limits.
It really is. For our listeners, FADEC systems electronically manage virtually all aspects of engine performance, fuel flow, ignition, variable geometry, etc., ensuring optimal thrust, fuel efficiency, and providing vital protection against exceeding limits like overtemperature or overspeed conditions. An inoperative FAD channel would seriously compromise this crucial automated control, making dispatch fundamentally unsafe.
And the air data systems.
Similarly, air data systems provide essential information like airspeed, altitude, and outside air temperature to both the pilot's displays and the aircraft's computers, including the FADC. Their full functionality is non-negotiable for safe flight and dispatch because so many other critical systems depend on their accuracy for proper operation.
Gotcha. Okay, regarding the hydraulic power system, when is the use of the auxiliary hydraulic pump specifically prohibited on the ground? And is its use permitted at all during flight?
The use of the auxiliary hydraulic pump is prohibited when the ground operating temperature is below -40°C. Seems related to fluid viscosity at extreme cold. And no, the use of the auxiliary hydraulic pump in flight is prohibited. It's primarily for ground use. Hashtag 2.9 ice and rain protection.
All right, moving into ice and rain protection systems. When must the anti-ice engine estab buttons be selected on? What are the temperature and visible moisture criteria? And which temperature reference should be used, SAA or RRAT, for ground versus in-flight operations? This is crucial for preventing ice buildup.
Okay, engine and stabilizer anti-ice. These buttons must be selected on when you are between the temperatures of +10°C down to -35°C and you are in visible moisture.
So +10 to -35°C and visible moisture, both conditions needed.
Correct. And for the temperature reference, you use SAT, static air temperature, for ground operations, and RRAT, ram air temperature, for in-flight operations.
That SAT versus RRAT distinction is an important one for getting an accurate temperature reading in different phases of flight, isn't it?
It really is. Visible moisture meaning clouds, fog, rain, snow, sleet, anything you can see within that specific temperature range, +10°C down to -35°C, creates the ideal conditions for hazardous ice formation on critical aircraft surfaces like engine inlets and stabilizer leading edges. Using SAT on the ground accurately reflects the ambient air temperature, which is what matters when the aircraft is stationary or moving slowly. However, RAT in flight reflects the temperature of the air as it's compressed and slightly heated by impacting the aircraft at speed. This ram air temperature is far more relevant for predicting the actual potential for ice accretion on flying surfaces during flight. It's a subtle but vital difference for making the correct decision on using anti-icing systems.
Okay. Now, except for specific ground pre-flight checks, what's the maximum SAT, static air temperature, allowed for operation of bleed air anti-ice systems when the throttles are above idle power?
The maximum SAT for operation of bleed air anti-ice with the throttles above idle is +20°C. You generally don't need it or want the performance hit above that temperature.
Right. What's the ground operation time limit for the pedostatic heat system? Can you leave it on indefinitely on the ground to prevent damage?
No, you shouldn't leave it on too long on the ground. You should limit the ground operation of pedostatic heat to 2 minutes maximum to prevent overheating and potential damage to the probes themselves.
Okay, 2 minutes on the ground. Can the aircraft's anti-ice systems actually be used to de-ice surfaces prior to takeoff? Meaning, can you use them to melt existing ice or snow that's already accumulated? And how must the anti-ice wing buttons be selected for operations up at very high altitudes, specifically above FL410?
Right, two important points there. First, anti-ice systems must not be used to de-ice surfaces prior to takeoff. They are anti-icing, not de-icing systems. Second, the anti-ice wing buttons must be selected O-off-F for operations above FL410.
Okay, that first point raises a crucial distinction. If the built-in anti-ice system isn't for de-icing, what is? How do you get rid of ice before takeoff?
That's where ground de-icing procedures come in. Pre-takeoff de-icing typically requires specialized de-icing fluids, often heated, applied by ground crews to physically remove any existing ice, snow, or frost accumulation. The aircraft's anti-ice systems, in contrast, are designed primarily to prevent ice from forming in the first place during flight by heating critical surfaces. Trying to use bleed air anti-ice to melt significant ground accumulation is generally ineffective and can waste fuel or even cause issues with refreezing.
And the wing anti-ice being off above FL410.
That suggests either a performance consideration or a system limitation at very high altitudes. Perhaps the bleed air demand impacts engine performance margins too much up there, or maybe there are thermal management constraints for the wing structure at those low ambient temperatures and high altitudes. Using these systems inappropriately, either for the wrong purpose or outside their certified envelope, could lead to reduced aircraft performance or even system damage.
Got it. Regarding boundary layer energizers, or BLEs, those little strips you see on the wing, what is the firm requirement for dispatch regarding these?
All boundary layer energizers, BLEs, must be present for dispatch. On the Sovereign, that means 9 per wing. You can't fly if any are missing.
Small but absolutely critical components for maintaining proper aerodynamic efficiency, especially near the stall.
Exactly. For our listeners, BLEs are small but precisely placed aerodynamic devices, often little strips, tabs, or vortex generators that help keep the airflow attached to the wing surface, particularly at higher angles of attack or in certain critical flight conditions. Their absence could negatively impact the aircraft's stall characteristics, reduce control effectiveness, or affect overall aerodynamic performance in ways the flight manual doesn't account for. That makes their presence a mandatory dispatch item to ensure safety and predictable flight behavior. Every little piece matters on an airplane. Hashtag 2.0 cabin baggage and thrust reversers.
Okay, let's talk about the cabin environment itself. What are the normal cabin pressurization limits in terms of differential pressure, PSID? What's the setting for the pressure relief valve, which acts as a safety backup? And what's the absolute pressure gauge red line?
Okay, the pressurization limits are normal cabin pressurization limits range from 0.0 up to 9.3 plus negative 0.1 PSID. That's the normal operating differential pressure range. The pressure relief valve is set slightly higher at 9.6 plus negative 0.1 PSID to prevent exceeding the normal limit. And the absolute pressure gauge, red line, the structural limit, is 9.7 PSID.
These limits are designed to ensure both passenger comfort and, crucially, the structural integrity of the fuselage under pressure loads, right?
Absolutely. Maintaining precise cabin pressure differential is critical. The normal operating limits ensure a comfortable and safe environment for passengers, typically maintaining a cabin altitude equivalent far lower than the aircraft's actual cruising altitude, preventing hypoxia and general discomfort. The pressure relief valve acts as a vital safety mechanism, automatically venting pressure if the normal control system fails, preventing the cabin pressure differential from exceeding the fuselage's structural design limits. And the red line indicates the absolute maximum pressure differential the fuselage can safely withstand before risking structural damage or failure.
Okay. When the press source selector is selected to L or R using a single bleed source, or when an ENG BLD air selector is selected O off F, or if an engine bleed air source is otherwise unavailable, how must the baggage heat button be selected?
In any of those situations where you might have reduced bleed air availability, the baggage heat button must be selected off, likely to conserve bleed air for more critical functions.
Makes sense. What is the maximum number of occupants permitted in the passenger compartment? How must the lavatory door be latched for taxi, takeoff, and landing? And what are the restrictions on actually using the lavatory?
The maximum number of occupants allowed in the passenger compartment is 12. The lavatory door, as we mentioned for takeoff and landing, must be latched open for taxi, takeoff, and landing phases. And critically, the use of the lavatory itself is prohibited for taxi, takeoff, and landing, and its use is strictly limited to one occupant at a time in flight.
These safety regulations around lavatory use during critical phases of flight are pretty standard across commercial and business aviation, aren't they? And the single occupant limit in flight is also common.
Yes, they are. These rules are primarily in place for safety. They ensure that all passengers are properly seated and secured with seatbelts fastened during the most dynamic phases of flight, taxi, takeoff, landing, making them ready for a potential emergency evacuation, if necessary. The single occupant limit in flight is often related to structural limits of the lavatory itself, weight and balance considerations, or sometimes emergency response procedures, ensuring quick access and safety within that confined space.
Okay, for the baggage compartment now, what systems must be operational if baggage is actually going to be carried back there? What's the maximum total weight of baggage allowed in the tail cone compartment? And what's the maximum floor loading distribution allowed?
Right, for carrying baggage. The baggage compartment's smoke detection and extinguishing systems must be operational if any baggage is to be carried. Non-negotiable.
Critical safety feature.
Absolutely. The maximum total weight of baggage allowed in the tail cone baggage compartment is 1,000 pounds. And the maximum floor loading distribution is 150 pounds per square foot. You can't just pile everything heavy in one spot.
Having smoke detection and fire suppression for the baggage compartment seems absolutely critical, especially since it's an area not directly observable by the crew or passengers.
It's incredibly important. It highlights the serious focus on cargo safety in aviation design. A fire starting in the baggage compartment can become extremely dangerous very quickly if it's not detected and suppressed automatically, as it's often completely inaccessible to the crew during flight. The weight and loading limits are equally essential, both to maintain the aircraft's overall center of gravity within its safe operating limits for stability and control, and also to prevent structural damage to the compartment floor itself, which could have catastrophic consequences if it failed.
Okay. Regarding thrust reversers, at what speed during the landing roll must reverse thrust be reduced to the idle reverse detent position? Is deployment for more than 30 seconds prohibited if the APU is operating? What's the limit for static ground operation of the main engines if the thrust reversers are deployed? And is the use of thrust reversers permitted during touch-and-go landings?
Okay, several points on reverser ops. Reverse thrust must be reduced to the idle reverse detent position by 65 psi during the landing roll.
Reduce power by 65 knots. Why?
Primarily to prevent FOD, foreign object debris ingestion, and also to minimize directional control issues at slower speeds. At lower ground speeds, the reversed airflow can kick up debris from the runway surface, which can then be ingested by the engines, causing potentially expensive damage.
Okay. What about the APU interaction?
Deployment of the thrust reversers for more than 30 seconds with the APU operating is prohibited, likely due to exhaust gas reingestion concerns for the APU.
And static ground offs with reversers deployed.
Static ground operation of the main engines is limited to IDL power only if the thrust reversers are deployed. You can't run up the engines statically with reversers out.
And touch and goes?
No, the use of thrust reversers is prohibited during touch-and-go landings.
Okay, that 65 Ks reduction makes sense for FOD and control. The APU limitation and static ground operation limit highlight specific operational constraints, maybe related to heat or airflow. And prohibiting reversers during touch and go seems logical. It prevents potential damage to the reverser systems from rapid cycling between deploy and stow, and it also simplifies pilot workload during what is already a high workload maneuver.
Exactly. It's all about calculated risk management and ensuring the operational longevity of the systems.
One more on reversers. Is the use of thrust reversers to actually back the airplane up, power back, prohibited? And when must takeoff performance data not be predicated on the use of thrust reversers, specifically due to ground operating temperature?
Yes, the use of thrust reversers to back the airplane is prohibited. You can't use them for power back operations. And takeoff performance data must not be predicated on the use of the thrust reversers for stopping distance calculations in case of an abort when the ground operating temperature is below -40 degrees C. There's a slightly higher temperature limit, magus to 15 degrees C, for very early serial number airplanes without a specific service letter incorporated. #2.11 display in avionics.
All right, nearing the end here, let's talk displays and avionics. For the standby flight display, your essential backup instrumentation, what's the core requirement for its functionality prior to takeoff?
The standby flight display, which needs to show attitude, altitude, and airspeed, and the associated standby HSI, horizontal situation indicator, must be functioning prior to takeoff. It has to work before you go.
Absolutely essential backup instrumentation. Can't stress that enough.
No, you really can't. The standby flight display provides critical, independent backup flight information in the hopefully unlikely event of a failure of the primary flight displays. Its operational status is a firm dispatch requirement because it ensures the crew has all the necessary basic attitude, altitude, airspeed, and heading information needed to safely navigate and control the aircraft, even if they experienced a complete loss of the main avionics suite. It's a fundamental layer of redundancy, an absolute lifeline for continued safe flight.
Okay. For the main avionics suite, the Honeywell Primus Epic system, what's the time limit for ground operation with the EIAC, Engine Indicating and Crew Alerting System, or other avionics selected on without conditioned air flowing, specifically when the OAT, outside air temperature, is greater than 47 degrees Celsius? What specific amber messages displayed would prohibit dispatch, and what post-flight condition also prohibits dispatch until it's corrected?
Okay, avionics cooling is critical. Ground operation is limited to 30 minutes with avionics powered up when the OAT is greater than 47 degrees C unless you have conditioned air providing cooling.
30 minutes max in the heat without air. Got it.
Dispatch is prohibited when any of the following specific amber messages are displayed. DU1234 OTEMP, which means display unit over temperature, or MAU1234 OTEMP, which means modular avionics unit over temperature.
So any overheat message for the main displays or computers grounds the plane.
Correct.
Yeah.
Furthermore, dispatch is also prohibited following a flight where either an amber DU OTEMP or MAU OTEMP message was displayed during that flight until the underlying condition that caused the overheat is identified and fully corrected by maintenance.
That makes sense. Don't just ignore a previous overheat warning. These specific temperature warnings and dispatch prohibitions fundamentally emphasize the sensitivity and the immense importance of proper cooling for modern, densely packed avionics.
They really do. Today's sophisticated avionics generate a significant amount of heat, and if they're not adequately cooled, especially in high ambient temperature conditions on the ground, they can overheat and potentially fail. These limits and prohibitions are there to ensure the operational integrity of the critical display units, DOUs, and the modular avionics units, MAUs, which are quite literally the brain and the eyes of the modern flight deck. Operating them outside these thermal conditions risks intermittent failures, permanent damage, or even critical in-flight failures. It's a non-negotiable aspect of system health monitoring.
Okay. Is reversion of both PFDs, primary flight displays, meaning both the left and right side PFDs, simultaneously displaying on the center screens, DU2 and DU3 permitted? How long must you wait to taxi after the attitude heading system completes its ground alignment? And what's the pilot seating requirement during all autopilot operations?
Reversion of both PFDs to DU2 and DU3 simultaneously is prohibited. You need at least one PFD in its normal position. Taxiing is prohibited until the attitude heading ground alignment process is fully completed. This takes approximately 90 seconds for the standard AHRS, attitude and heading reference system, or about 6 minutes if the optional IRS, inertial reference system, is installed and aligning.
So wait for the alignment complete message.
Absolutely. And crucially, one pilot must remain seated with their seatbelt fastened during all autopilot operations.
That pilot seating requirement during autopilot use seems like a fundamental safety measure, ensuring someone is always ready to intervene instantly if needed.
It is. If both primary flight displays were allowed to revert to the central display units, it would severely compromise the pilot's immediate access to their primary flight critical information in their normal scan pattern. The ground alignment period is vital. It ensures the aircraft's navigation and attitude reference systems are fully initialized and providing accurate data before any ground movement begins, which is critical for safe taxi and takeoff. And keeping one pilot buckled in and attentive during autopilot operation ensures that a human is always physically ready to take over manual control immediately if the autopilot malfunctions, disconnects unexpectedly, or if an unforeseen situation requires immediate pilot intervention. It's about maintaining human vigilance as a backup to automation.
Under what specific conditions is autopilot operation prohibited? Thinking about system health, like comparison monitor enunciations, PFD reversions, or attitude heading source failures. And related to vertical navigation, is barometric VN AV vertical guidance permitted when using QFE altimeter settings?
Okay, autopilot engagement is prohibited under several conditions. If any comparison monitor enunciation is activated, indicating disagreement between redundant sensors. If either PFD is in an ATT attitude or HDG heading reversionary mode, or if either attitude heading source, AHRS or IRS, has failed. Basically, if the core inputs are unreliable, don't use the autopilot.
Makes sense. Garbage in, garbage out.
Exactly. Furthermore, the use of barometric VNAV vertical guidance is prohibited when the barometric altitude source is set to QFE, which is the landing field elevation datum.
Why no VNAV with QFE?
Well, these are all very clear safety guardrails for autopilot use, ensuring it's only engaged when its underlying sensor systems are fully functional and providing reliably accurate data. Comparison monitors confirm that redundant systems agree. PFD reversion, or failed attitude heading sources, mean the autopilot's fundamental input data is compromised, making its use potentially unsafe or unpredictable. For our listeners, barometric VNAV systems typically calculate vertical paths based on altitude above mean sea level, using QNH altimeter settings. Using VNAV with QSE, altitude above the airfield, would lead to incorrect vertical guidance calculations during an approach, creating a significant and dangerous safety risk. It's about knowing the limitations of the data you're feeding the automation system.
Okay. What are the autopilot minimum use heights? The lowest altitudes you're allowed to use the autopilot during different phases of flight. En route and descent, a precision approach like an ILS or LPV, a non-precision approach, and during takeoff, climb, and missed approach phases. Also, is autopilot operation permitted during in-flight engine starts that require using starter assist?
Okay, the autopilot minimum use heights are, for en route and descent, it's 1,000 feet AGL. For a precision approach, like ILS or LPV with vertical guidance, it's 80 feet AGL. For a non-precision approach, it's 200 feet AGL. And for takeoff, climb, and missed approach phases, it's 400 feet AGL. And no, autopilot operation is specifically prohibited during in-flight engine starts that are using starter assist.
These minimum heights seem to reflect the level of automation deemed acceptable during different critical phases, essentially requiring the pilot to take manual control below those specific altitudes.
That's precisely it. These limits are carefully designed to ensure that human pilots are in direct manual control during the most critical and dynamic phases of flight, close to the ground, where rapid decision-making, precise manual inputs, and visual references are absolutely paramount. Prohibiting autopilot use during engine starts involving starter assist is likely due to the fluctuating electrical loads and potential system reconfigurations that occur during the start sequence, which could lead to unpredictable or potentially unsafe autopilot behavior.
Yeah.
Again, it's about ensuring human oversight and control precisely where and when it matters most.
Is configuring the airplane displays to show metric fuel and weight units prohibited? When you're changing VOR or ILS frequencies while the flight director or autopilot is coupled to the navigation source, what mode must be selected first, and what mode can be re-engaged after you've confirmed satisfactory reception of the new frequency? And lastly, are HF radio transmissions prohibited when your primary navigation is predicated on using the ADF automatic direction finder?
Okay, configuring the airplane displays to metric fuel and weight units is prohibited. Stick to pounds and gallons U.S. units. When the flight director or autopilot is coupled to VOR or ILS navigation, HDG mode, heading mode, must be selected prior to switching navigation frequencies. Then, after tuning the new frequency and confirming satisfactory reception, NAV mode may be re-engaged. And yes, HF radio transmissions are prohibited when navigation is predicated on the use of the automatic direction finder, ADF.
Okay, the metric units prohibition is likely just a standardization requirement for the type certificate or operator, ensuring all operational data is presented consistently.
Probably, yeah. Consistency reduces errors.
That procedure for changing nav frequency switching to HGG mode first seems like a clever safety feature. Why is that done?
It is. It prevents potentially uncommanded and abrupt turns if the newly tuned frequency is not immediately valid, or if there's a momentary signal loss during the switch. By selecting HDG mode, the aircraft simply maintains its current heading while the pilot tunes and verifies the new navigation source. Once confirmed, re-engaging NAV mode allows the autopilot or flight director to smoothly capture and track the new course. It avoids potential surprises.
And the HF transmission prohibition with ADF.
That's due to a known interference issue. HF radio transmissions operate at frequencies that can generate electromagnetic interference, which can corrupt the relatively weak signals received by the ADF system, leading to inaccurate or erratic needle bearings. This prohibition prevents pilots from relying on potentially erroneous navigation information from the ADF when the HF radio is transmitting, which could be very dangerous, especially during an instrument approach.
Final area, electronic charts. For airplanes equipped with them, Can the geographic referenced airplane symbol shown on the chart display actually be used for primary navigation? What must operators always have available to the flight crew as a backup? What specific currency must be verified before using the electronic charts? And crucially, who holds the responsibility for verifying that the necessary charts are actually available for the planned flight?
Okay, important points on electronic charts. When displayed, the geographic referenced airplane symbol on the optional electronic charts must not be used for primary navigation. It's for situational awareness only. Operators must have backup charts available to the flight crew. This could be paper charts or perhaps a secondary electronic flight bag.
A backup is mandatory.
Mandatory. The data start date currency must be verified on the chart's revision info window prior to use to ensure the chart information is current. And critically, the flight crew is responsible for verifying the availability and currency of all charts needed for the planned flight, whether electronic or paper.
This really highlights a foundational principle in modern cockpits. Even with incredibly advanced electronic charts, they are often primarily designed and certified for situational awareness, not necessarily as the sole means of primary navigation. And traditional backups remain absolutely critical.
Absolutely. It raises that important question again. Why isn't the on-screen symbol suitable for primary navigation? And what are the real-world implications of relying solely on electronic charts without proper backup and verification? Electronic charts, while incredibly convenient and powerful, might not be certified to the same stringent accuracy standards as primary navigation instruments, or their display might lack the precision required for sole reliance in critical phases like final approach. The requirement for physical or secondary backups and explicit currency verification underscores the enduring importance of reliable, validated navigation information. It emphasizes that technology is a powerful aid, but it doesn't completely replace the need for fundamental flight planning, cross-checking, and traditional navigation methods or backups. It's all about maintaining multiple layers of safety.
Wow, that was quite the deep dive, wasn't it? Right into the Citation Sovereign's operational heart. We've really navigated through some crucial emergency procedures, from those immediate reflexive actions during APU fires to the more nuanced responses for things like uncommanded thrusts.
Yeah, and then all the limitations.
Exactly. And we explored those non-negotiable boundaries set by its operational limitations, covering pretty much everything from foundational weight restrictions to the intricate rules governing complex avionics systems and their interactions. Every single detail we covered today is an absolute cornerstone of safe flight in this aircraft.
It really is.
Yeah.
And if we kind of connect this to the bigger picture, it just profoundly underscores the immense responsibility and, frankly, the level of precision involved in piloting a modern high-performance aircraft like the Sovereign.
It's not just stick and rudder anymore.
Yeah, not at all. It's not merely about knowing how to fly. It's about a deep, intuitive, and constantly practiced understanding of every single system, every limit, and every emergency procedure. It really raises an important question for all of us, I think. Just how many layers of knowledge, rigorous training, and constant practice go into every single flight, transforming what could be an incredibly complex machine into, well, a symphony of controlled movement.
That's a great way to put it.
And, this level of precision and constant readiness, it extends far beyond aviation, doesn't it? You see it in fields like medical surgery or complex civil engineering projects, where meticulous adherence to established limits and procedures ensures our safety and well-being every day.
It's truly fascinating to see how meticulously these aircraft are designed, tested down to the smallest detail, and then how equally meticulous the training has to be to ensure that the human factors, the pilot proficiency, flawlessly meet the machine's capabilities.
Yeah, the human-machine interface is key.
Knowing these details isn't just for pilots cramming for a check ride. Hopefully it gives all of you listening an aha moment about the incredible science, the discipline, and the sheer dedication that keeps air travel as safe as it statistically is. Think about the rigorous testing and retesting that goes into defining each one of these limitations we discussed, sometimes pushing the aircraft to its very edge in a controlled environment, all so that pilots, and by extension passengers like us, can trust these systems implicitly day in and day out.
Built on layers of safety analysis.
Absolutely. So maybe a final thought for you to ponder. What's one critical limitation or procedure in your own field, or even just in your daily life, that, if ignored, could lead to some unexpected or potentially serious consequences? Something we often take for granted. Whether you're diligently studying for your check ride, maybe prepping for a high-stakes meeting where knowing the limits is key, or perhaps you're just immensely curious about the precision required in modern aviation. We really hope this mock check ride, this deep dive, has given you a clearer, more thorough, and genuinely insightful understanding of the Citation Sovereign. Keep that curiosity firing, keep learning, and keep exploring the incredible world of knowledge with us. Until next time.